Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we'll discuss poles and zeros of analytic function, how one can relate, and also the behavior of analytic functions near, or not only analytic function, any function near isolated singularity. Okay, let's start. Uh, Last class we have defined what is meant by a pole. In the principal part, if we have finitely many, then we say that that singularity is a pole. Okay, so now we'll give characterization of when a isolated singularity is a pole. So we say that an isolated singularity z naught is a pole, okay, of order m if and only if, so this z naught is a pole, okay, pole of order m if and only if or f of z can be written of the form phi of z upon z minus z naught whole power m, where this phi is I'm sorry, analytic at z naught, okay, and phi of z naught is non-zero, okay. And in this case, that means when z naught is a pole of order m, then the residue, we can calculate residue of f of z at z naught, z is equal to z naught. This is simply in terms of phi, that is m minus 1 derivative of phi evaluated at z naught by m minus 1 factorial. Okay, this is true for m greater than or equal to 1. That means even in m is equal to 1, it is simply phi of z naught. Okay. Fine. What is the proof? Proof is not at all difficult one. Suppose assume that we have this expression. Suppose if f of z, okay, if f of z is of the form phi of z upon z minus z naught whole power m, where phi of z is analytic. Now, what we know, when any analytic function is there at a, suppose something is analytic, then it has a Taylor series representation. So therefore, our phi of z can be written as phi of z naught, phi dash of z naught by 1 factorial to z minus z naught and so on. And here from m onwards, okay, this we have clubbed into one series and kept it, right. Now therefore, if phi of z has this Taylor series expansion, then f of z, which is phi of z by z minus z naught whole power m, that means whatever we are having here, you divide that by this z minus z naught whole power m to get our f of z. That is this one, okay. Now if you observe here, because here z minus z naught whole power n is there, when you divide by m, you will get n power m minus m, okay. Now you have 1, 2, 3, some finitely many terms here, which are negative powers of z minus z naught, and then whatever we are having here is positive powers, okay, non-negative powers, right. So that shows that, and not only this, what we know about phi of z naught? Our phi of z naught here is non-zero, right. So therefore we have this coefficient of 1 upon z minus z naught whole power m, which is this phi of z naught, which is non-zero, right. So therefore this is a Lorentz series expansion, right. As phi of z naught is not equal to 0, the coefficient b of m, which is phi of z naught, is non-zero, okay. So here we are getting that b of m is non-zero, but after that b of any m plus I equal to 0, that shows that this is a pole of order m, okay. Fine. Now what about converse? Same way. Take, suppose assume that we have, conversely suppose assume that z naught is a pole of order m, okay. Sorry, this is when pole of order m, and why it is residue is this one, because this coefficient of b1, coefficient of b1, if you write, see here, this is the coefficient of b1, okay. This is the b1, which is coefficient of 1 upon z minus z naught, and that is the residue, right. Now suppose assume that conversely z naught is a pole of order m, okay. That means what, we know that bm is non-zero, after that all our terms are 0, so maximum this many terms will exist, okay, where bm is non-zero, okay. Now using this f of z, we want to get our phi of z, right. So we can define phi of z as z minus z naught, because whole power m into f of z, that we define as our phi of z when z not equal to z naught, okay. When z is not equal to z naught, we define phi of z is like this. Therefore, f of z will become phi of z by z minus z naught whole power m. Right? When z is equal to z naught, our phi of z should be equal to, define that as bm. Okay. Then we can see that this phi of z has this phi of z, because that means you multiply this whatever we are having here, this you multiply by z minus z naught whole power m. Okay, we get a expression, right? That is this, because bm plus bm minus 1 into z minus z naught and so on, and you have here, right? That means if you consider this, by when multiplying by z minus z naught whole power m, first term is bm, then next term you will have one less, so z minus z naught and so on, right? So you can see that it is a Taylor series expansion. Therefore, this phi of z is analytic in that disk, in particular at z naught. And also you can check that phi of z naught, when you substitute z naught here, that is same as this b of m, which is non-zero here, because our assumption is that this f, this z naught is a pole of order m. That's why our bm is non-zero, that I have written here, right? Bm is non-zero. That means phi of z naught is non-zero. Okay. So what we have seen is that is isolated singularity is a pole if and only if that function has the representation phi of z upon z minus z naught whole power m, where that phi of z is analytic at z naught. Okay. Fine. Let's quickly see one example. If you see one example, this f of z is equal to z plus 1 by z square plus 9. So this you can write into z plus 3i into z minus 3i. So 3i and minus 3i, these are two isolated singularities. So consider z is equal to 3i. Now we can represent this f of z in as this f of z, we can write this as z plus 1 by z minus 3i, okay, divided by z plus 3i. Okay. So you want to talk about at 3i, this is same. So here you write z plus 3i and here z minus 3i. Now you call it this as phi of z. Okay. Then you can check that this phi is analytic at 3i. There is no problem at 3i. So therefore this phi is analytic at 3i, and phi of 3i. Phi of 3i, you can check that it is clearly non-zero, right? So therefore this f has a pole, namely simple pole at z is equal to 3i, and residue you can calculate, you will get this as residue of f of z at z is equal to 3i is 3 minus I upon 6. Okay. So residue of this f of z, whatever we have there at z is equal to 3i, by substituting this using that formula, what you will get is 3 minus I by 6. Same way you can do it for at minus 3i also. Only thing is here minus 3i will come, here plus 3i will come, and when you substitute calculate residue, you will get 3 plus I by 6. That one can check. Okay, fine. Let's take another example, which is f of z cube plus 2z upon z minus I whole cube. So you can see here that z is equal to I is a singular point. Z is equal to I is a singular point. So therefore, if you simply take this much as our phi of z, which is z cube plus 2z, then clearly we know it is a polynomial, so it is analytic everywhere. So in particular at I also it is analytic, and phi of I is non-zero. So therefore, what is residue? So residue of f of z at z is equal to I, this is nothing but, because this is phi and we have here m, right? So m minus 1, that means phi m minus 1, which is 2 by 2 factorial. Okay, that means this is phi of z, find 2 times derivative, then substitute I there. Okay, what we will get is this. The answer is 3i. So the calculation I'll skip, you can find out. Okay, now we'll come to zeros and see how analytic function zeros are related. Okay. So take suppose now here f is analytic at z naught. F is a analytic function at z naught. Suppose that f of z naught is equal to 0, okay, which is same as f dash of z naught up to say f m minus 1 derivative evaluated at z naught, they are all equal to 0. But f mth derivative when evaluated at z naught is non-zero, suppose. Then we say that this, because clearly z naught is a 0, right? Not only that, after derivative, first derivation substituting z naught is 0, up to m minus 1 the derivative is 0, but at mth derivative evaluation at z naught is non-zero. So this shows that it is a 0 of order m. Okay, so we say that this z naught is a 0 of order m if up to f of z naught including f of z naught, then up to f m minus 1 of z naught, if they all should be equal to 0, but f m of z naught is non-zero. Okay, because here which is like we are starting from 0th derivative, just like that. Okay, 0 up to m minus 1, so there include total m are there, right? That's why it is of order m. Then just like what how we have here for a pole characterization for zeros of analytic function, also we can have characterization, namely if we take f analytic at z naught, then this z naught is a 0 of order m if and only if, so this is a order z naught, okay, is a 0 of order m if and only if f of z can be factorized and written as z minus z naught whole power m into g of z, where g of z is analytic and g of z naught is non-zero. So here g is analytic and g of z naught is non-zero. So this is analytic, g is analytic, and g of z naught is non-zero. That means you cannot take out z naught further here. Okay. This proof is again not a difficult one. Here you can see this is, suppose f of z is of this form. If f of z is of this form, then we want to show that this z naught, okay, is a 0 of order m, right? So if this is here, and because g is analytic at z naught and it is non-zero, we have a Taylor series representation. So write g of z as a Taylor series representation. Then you multiply this factor z minus z naught whole power m to this g of z, that you will get f of z. Okay, so you can see here this is g of z into z minus z naught whole power m plus 1 and so on. Okay, so this is again Taylor series. Okay, there are no negative terms here, right? Taylor series for this f of z, that means itself says that if you write this f of z as summation a n z minus z naught, f of z as summation a n z minus z naught whole power n, then you can see here it is starting from m. Okay, the power of z minus z naught starts from m plus 1 and so on. That means what? Before m minus 1, all coefficients are 0. That shows that this such that all coefficients a k is from 1 up to m minus 1, they are all 0. Okay, even you can write here not only 0, so you can write from 0 1 2 up to m minus 1, they are all 0. And am, that means when k is equal to m, what you will get here is g of z naught. Okay, that one can take here, right? That this ak, because of this we get that ak is equal to 0, right? And am is equal to g of z naught. So but what are all ak by this in this Taylor series expansion? Formula for each ak is fk of z naught upon k factorial. That shows that fk of z naught is equal to 0 for all k, and fm of z naught, which is equal to m factorial into g of z naught, not equal to 0. That shows that this fm of z naught is non-zero, but up to m minus 1 they are all 0. So therefore z naught is a 0 of order m, right? Conversely, what we want to, so suppose assume that this z naught is a 0 of order m, that means up to first f of z naught, then f dash of z naught up to f m minus 1 of z naught, they are all 0, and f m of z naught is non-zero. Okay, now because we already know that f is analytic, so try to write the Taylor series expansion. Okay, and substitute the values of fn of z naught up to m minus 1, they are all 0, so it starts from m onwards, so that you can see that n is equal to m to infinity, this one, right? Now here in every term z minus z naught whole power m will be there, because m, then m plus 1, m plus 2 and so on. So take out z minus z naught whole power m outside, and whatever is remaining, that you call it as this g of z. Okay, then we can check that, because after even taking common, this is still a Taylor series of this function. So therefore not only Taylor series, it is just a power series, so therefore it is analytic. So this is analytic at z naught, and g of z naught is not equal to 0 because one coefficient will be there, first coefficient, that is fm of z naught, but we know fm of z naught is non-zero here, okay, right? So therefore this g of z naught is non-zero, right? So very simple. If we many times we use Taylor series representation, Lorentz series representation, and we play here and there. Okay, that's why those are all very important. Okay, if you see from last two classes, we are using the results which we have proved already. We are not using anything new. We are properly putting the results such that we get our required results. Okay, fine. Now this is one interesting result we have here, which is just like uh, if we have an analytic function, then the under some conditions, zeros of analytic functions can also be isolated. Okay, so this result is about zeros which we can separate in different neighborhoods, zeros of analytic function. So what it says is that if f is analytic at z naught, okay, and f of z naught is 0, that means z naught is a 0 of f, okay, but f of z naught is not identically equal to 0 in any neighborhood of z naught. So you take any neighborhood of z naught, okay, at least at some point this is non-zero, any neighborhood you take, but f of z naught is 0, right? Under these two conditions, then we can say that there exists, so there exists a neighborhood, there exists a neighborhood of z naught, deleted neighborhood, such that if you take any point here, this is non-zero. F of z is not equal to 0. Here f of z is not equal to 0 for all z in this neighborhood. What is the meaning of that one? This z naught, we know z naught is a 0 of that f. Okay, so we are able to separate this 0 from other zeros with the help of this one neighborhood. Okay, that's why this 0 is isolated. So this result is about when we can isolate zeros. So it only requires that f is analytic at z naught and f of z naught is 0, okay, such that f of z is not identically equal to 0 in any neighborhood, because if it is equal to 0 in some neighborhood, then we cannot separate that, right? Fine. Proof is, again, it is not a difficult one. Whenever we have f is analytic at a point, ready made, we have a Taylor series representation. So right, f is analytic at z naught, so we have f of z, which is equal to summation an, that is f nth derivative of z naught upon n factorial z minus z naught whole power n. Of course, this is in this domain. Okay. Now, if at all, this is very important, if at all f n of z naught, if it is equal to 0 for all n, okay, for all n, then this f of z will become 0 here, right? This implies f of z equal to 0 here, right? But that is not true, because we have assumed that it is not identically equal to 0 in any neighborhood. That shows that what, there exists some m such that fm of z naught is not equal to 0, right? Fm of z naught is not equal to 0. Now that means uh, we have one stage definitely where fm, especially m, such that fm of z naught is non-zero. Now what we'll choose k, so we will choose k such that this fk of z naught is not equal to 0, and before that all are 0, and this f1, okay, f1 of z naught up to fk minus 1 of z naught, they are all equal to 0. So choose k, which is of course less than or equal to m, such that fk of z naught is not equal to 0 and remaining all are 0. So the idea is, here we already have one stage m where this is non-zero. What we are going to see is, can we go back, right? If it is possible, find k such that this fk of z naught is still not equal to 0, but before that all are 0. Okay, and if no such k before m exists, then obviously our k is equal to m, because we know already fm of z naught is not equal to 0. So definitely such k exists, right? Either that k may be smaller than m or at most equal to m, right? So from here, what we can conclude from this itself shows that this z naught is a 0 of order k, right? So therefore this z naught is a 0 of order k, right? Then by previous result here, if it is a 0, right, we can write that as, by we can take out that z minus z naught whole power k term outside. So f of z we can write as z minus z naught whole power k into phi of z, okay, where phi of z is analytic and non-zero at z naught. That means phi of z naught is not equal to 0. Now because this phi of z is analytic, that in particular f this phi is differentiable at z naught, so this phi is continuous at z naught. So we have already a result that if phi is continuous at z naught and this phi of z naught is not equal to 0, right? So therefore the result which we have proved, a continuous function, if it is not equal to 0 at that point, then there exists a neighborhood around of that point. Throughout in that neighborhood, this function is not equal to 0. That we have proved. So there exists some neighborhood which is z minus z naught less than epsilon, okay, in which phi of z is not equal to 0. Okay, so this epsilon and this you can, if you want, you can change. So that you can write here there exists delta in which phi of z is not equal to 0. If phi of z is not equal to 0, then in this diluted neighborhood, this f of z, z minus z naught whole power k times that, which is also not equal to 0. That proves that there exists a neighborhood where f of z is not equal to 0 in that neighborhood except at z naught, right? So that 0 we are able to separate from other zeros, right? Now this result, if we remember when we discussed about reflection principle, this result we have used there, okay? Now we will prove that result. What it says is that if a function f is such a way that f is analytic throughout a neighborhood of n naught, so f is analytic throughout n naught, which is the neighborhood of z naught, okay, and f of z is equal to 0, okay, for all z belongs to that subdomain, okay, or for all z belongs to that L, both this either subdomain or that line should contain this point z naught, okay, then we can say that f of z is actually 0 in this entire neighborhood n naught, okay. Fine. So this is what we want to prove, that means for an analytic function, if it is 0 on a line or 0 on a subdomain, then we are saying that it is 0 on the whole domain, okay. That means here we are not able to separate zeros in this theorem, right? Fine. Now what first we will show that f of z is 0 in some neighborhood, okay, not necessarily n naught, but if you prove it is true for some neighborhood, then it is also true for this n naught, okay. How we will prove that? F of z is equal to 0. We want to show that f of z is equal to 0 in some neighborhood of z naught. Suppose not, so that means f of z is not equal to 0 in every neighborhood, for all neighborhoods of z naught, okay. But we know that f of z naught is equal to 0 because z naught is a particular point of D, also a point of L. So we know f of z naught is equal to 0, but f of z is not equal to 0 for all every neighborhood of z naught. That means at least there is one point in that neighborhood where f of z is non-zero, okay. So that we can apply this result now. So if we can apply this result, what it says is that in particular there exists a neighborhood, okay. So you can see that in particular f of z is not equal to 0 in some neighborhood of z naught containing that domain D, right? By this result, there exists a neighborhood where f of z is not equal to 0, so which is a contradiction to this assumption of B. Let me repeat again. Suppose f of z, we want to show that f of z is equal to 0 throughout some neighborhood. Suppose not, that means what? F of z is not equal to 0 at every neighborhood of z naught. Remember, f of z is not equal to 0 means we are not talking about at every point. At least there will be one point in that neighborhood where f of z is non-zero. And we know already z naught is a 0. So f of z naught is equal to 0. So by previous result, there exists some neighborhood of z naught, okay, such that f of z is not equal to 0 throughout that neighborhood. Okay. But that is the contradiction to the point B, because what it says, if you have any domain, okay, containing that z naught, then f of z should be equal to 0 for all that. But that is not the case we are getting here, right? So therefore what is true is that f of z is equal to 0 for some neighborhood of z naught, right? Then again, because f is analytic throughout this neighborhood n naught, so therefore this f has a 4-point representation or Taylor series representation around this point z naught. So write f of z, that is this one. Okay, this is f of z is equal to summation fn of z naught by n factorial z minus z naught whole power n. But we know on this n it is 0, so this is equal to 0, right? When this will be 0, if and only if all these coefficients fn of z naught by n factorial, this should be equal to 0, right? So because all these coefficients are equal to 0, even in n naught, if you take, even in n naught, because f is analytic throughout this neighborhood n naught, so what we'll have, the Taylor series representation of f around z naught in this neighborhood n naught, the coefficients will be same, this fn of z naught by n factorial only. There is nothing difference, right? So but all those coefficients are 0, so therefore f of z is equal to 0 in n naught also, right? So that proves that f of z is equal to 0 in n naught, right? So this proof follows from this, that at least there will be one neighborhood, okay, in which f of z is completely 0. That is follows by proving contradiction. Suppose not, then it says that there is at least one neighborhood, okay, where throughout it is non-zero, but that contradicts this point B. Okay. Fine. Now as I said in last class, we will see some relation among zeros and poles. Okay, that means zeros, some point is a 0 of some particular order, then that point will be a pole of some other new function. What is that function? We'll see here. Okay. Suppose assume that P and Q are analytic functions at z naught. Okay. And P of z naught is not equal to 0, and Q has a 0 at z naught of order m. Okay. So Q has 0 of order m at z naught. That means this z naught is a 0 for this function q of z. Then this z naught, is a pole of order m for the function which is p of z by q of z. Okay. So if we have some point is a 0 of order m, then that point is a pole of a new function which is p of z by q of z. Okay. What is condition required is that p and q should be analytic, p of z naught is non-zero, and q has a 0. This z naught is a 0 for this function q of order m. Okay. And it is again every time, most of the time, what we do is, if it is not analytic, if it is analytic, then we use previous results. If it is a pole, then we use previous result. If it is a 0, then we use, and we will write it properly. Here you can see that since q is a analytic at z naught, and z naught is a 0 of order m, so what we can observe here is that, go to this result here. This q is analytic at z naught, and z naught is a 0. Q of z naught is equal to 0. So therefore q of z naught is equal to 0, right? That shows that there exists a neighborhood. So there exists a neighborhood in throughout which q is non-zero. Okay. So that is what we are writing here. So throughout some deleted neighborhood of z naught, q is not equal to 0. Okay. Here q is not equal to 0 there. So that means what you can see is that there is some deleted neighborhood of z naught, right? We know this uh, z naught. Now if you take this p of z by q of z, for this clearly z naught is a singular point. Z naught is a singular point for this p of z by q of z, okay? And we are able to find some neighborhood where this q of z is non-zero. So therefore this p of z by q of z is analytic everywhere in this deleted neighborhood. That means what? This z naught is a, so this z naught is an isolated singularity. Okay, that means we are able to separate that singularity for this function p of z by q of z, right? So therefore z naught is an isolated singularity of this function p of z by q of z. And also because this q, for this function q, this z naught is a 0 of order m, we can write this q of z as z minus z naught whole power m into some function which we can write as g of z, where g is analytic and g is non-zero at z naught. Okay, so therefore p of z by q of z, what we'll get? Therefore p of z by q of z, this we can write this as p of z upon z minus z naught whole power m, okay, by g of z. Okay, just split like this. That means you call it this as phi of z. Okay, then this phi of z is sorry, you write it in reverse. This not here. We write this as g of z and z minus z naught whole power m. Okay, so this is of the form phi of z by z minus z naught whole power m. So that itself is enough if we want to prove that this z naught is a pole of order m. We have proved the first result today, that if a function has of this expression, then z naught is a pole of order m. So that shows that z naught is a pole of order m, right? So that is how it plays. If something is a 0, then that point is a 0 pole of another function, namely p of z by q of z. Now here we can calculate for a simple pole. It is similar to the, we can say it follows from here. What this result says that if we have two functions which are analytic at z naught, and if p of z naught is not equal to 0, q of z naught equal to 0, but q dash of z naught is not equal to 0, that means what? Z naught is a simple pole. Okay, simple pole for this function q, right? Then z naught is a simple pole. This is, sorry, this is simple 0. This is a simple 0 for this function q of q. So therefore z naught will become simple pole for p of z by q of z, and in this case residue of this function p of z by q of z at z is equal to z naught is simply given by p evaluated at z naught by q dash of z. Okay, and this follows just by this previous result. Okay, because it is 0 of order 1, so you can express in this form. Only thing is q dash of z, because of this q of z you differentiate this, so what we'll get is q dash of z is this. Therefore find the value of q dash of z naught, this term will vanish. So g of z naught is same as q dash of z naught that you will get, right? Fine. So you can call it, instead of this theorem, you can simply even write it as a corollary also. Okay, but for a simple pole we can calculate easily this residues. Fine. Let's see quickly an example to understand. If we take f of z, which is equal to tan hz by z square. Okay, the idea is try to write numerator and denominator in such a way that denominator you have a 0 and right at z is equal to pi I by 2. This you can simplify further into sin hz by z square into cos hz, right? Then if you take this as p of z, this you take as p of z, and this you take as q of z, then at z is equal to pi I by 2, you check whether p of pi I by 2, which is I not equal to 0, and q of pi I by 2 is equal to 0. And if you see q dash, which is non-zero, that means this pi I by 2 is a simple pole. Okay, so therefore you can find residue is simply p of that point divided by q dash of that point, which is minus 4 by pi square. Okay, those calculation you can do it, it is not a bigger one. Now we'll come to the last section of this one, which is very interesting. the behavior, we'll see how the behavior of functions, behavior of a function near this isolated singularities. So isolated singularities. So what are all we know? Three types of isolated singularities. One is pole, okay, then removable singularity, then essential singularity. So that means if some z naught is a pole of a given function f, what can you say about f near to that point? What value of f or how f behaves in a neighborhood of that z naught? Okay. Similarly, if z naught is a removable singularity, what can you say about f near to that point? If it is an essential singularity, what can you say about f near that neighborhood? Okay, fine. First one, let's start with if our f this z naught is a pole of given function f, then that means if we have a pole at z naught, this implies if you find the limit of f of z at z tending to z naught, this is infinite. That means this f approaches to point at infinity when z is near to the pole. Okay, that is this one, and it is not at all difficult to prove. Whenever we have discussed the basic beginning lectures, if we want to deal with infinity, try to deal by taking 1 by z, right? So this is same as proving that, this is same as proving what limit 1 f of 1 by f of z. That means we want to show that f of z tends to 0. So show that 1 by f of z tends to 0 as z tending to z naught, right? Now z naught is a pole for this function f. So therefore f of z can be written in this form because it is a pole. So we can write this as f of z in equal to phi of z, phi z by z minus z naught whole power m, where phi is analytic and non-zero at z naught. Okay. Therefore, what is 1 by f of z? So 1 by f of z will be z minus z naught whole power m by phi of z, right? Where phi of z naught is not equal to 0. So you can see that when z is equal to z naught, this value is 0, right? That shows that this limit z tending to z naught 1 by f of z. So this tends to 0 as z tending to z. That proves that at poles f of z is very near to point at infinity. Okay. Next, second result is when our singularity is a removable singularity. Okay. So if z naught is a removable singularity of given function f, then f is analytic and bounded in some deleted neighborhood. Okay. So suppose if z naught, this is a removable singularity of the given function f, then we can say that there exists a deleted neighborhood of z naught. Okay, you can call it epsilon or delta, no problem, where this f is analytic and bounded. Okay, fine. How we'll prove this? Because z naught is a removable singularity. What is meant by saying that it is a removable singularity? In the what is Lorentz representation, the principal part is 0. There are no terms in principal part, right? So therefore f of z is, you will having only positive powers of z minus z naught. Okay, that means of f of z, how it will be a naught plus a1 into z minus z naught plus a2 z minus z naught whole square plus and so on. Okay, where in deleted neighborhood mod z minus z naught is less than r. So in particular, how we can make this is analytic, because it has a problem only with z naught, right? So by defining f of z naught, as simply when z approaches to z naught, all these terms goes to 0. So therefore define f of z naught as simply a naught. Okay, then we can see that this f is analytic at z naught. So in particular, and it is analytic in mod z minus z naught less than r. Okay, because it is analytic everywhere here already, and it is analytic at z naught. So therefore it is analytic here, right? So in particular, it is continuous in any closed disk if you take inside this one. Okay, but we know when something is closed, then it is bounded, which we have proved that result. So therefore f is bounded in mod z minus z naught less than or equal to epsilon. Okay, and hence f is analytic and bounded in 0 less than mod z minus z naught less than epsilon. Okay, that shows that whenever we have a removable singularity, then there exists a deleted neighborhood in which f behaves not only analytic, it even bounded. Okay, fine. So at poles, this f is very very close to point at infinity, and at removable singularities there is a neighborhood of z naught where f is analytic. Okay, now we come to the last singularity, which is essential singularity. So to discuss about how f behaves when it is when we have a essential singularity, for that we first prove a lemma, then we go to that result. So this lemma or theorem is due to Riemann. So what it says is that if we have an analytic and bounded function, okay, in some deleted neighborhood. So suppose we have assume that that means whatever conclusion we have here, that, okay, that means whatever conclusion we have here, if that is true here, if f is analytic and bounded in some deleted neighborhood of z naught, okay, and if f is not analytic at z naught, if f is not analytic at z naught, then obviously that point will become a singular point, and only choice for that singular point is it has to be a removable singularity. Okay, if f is if f is not analytic, if f is not analytic at z naught, but f is analytic everywhere and it is also bounded in this interval, then only option is that z naught is removable singularity. Okay, how we can prove? It is not at all difficult one. So suppose f is, because f is not analytic at z naught, but it is analytic throughout this annular region 0 minus z naught is less than epsilon. So we have a Lorentz series expansion. We can write f of z is equal to summation an z minus z naught whole power n plus summation bn by z minus z naught whole power n, where this ans and bns can be calculated using integrals where c is any closed contour in between that annular region. Okay, so now what we will take here is, we'll take this c, we'll take that c as, so if you let me put it to see this image. Let me enlarge that image little bigger so that we'll reduce again further. Fine. Now what is our c? We'll take c around z naught, which is a positively oriented circle. So our c is mod z minus z naught is equal to rho, where rho is less than this. See, we already have a deleted neighborhood epsilon, okay, of radius epsilon. So you take a rho which is smaller than that. Okay, that means we are having a circle inside that deleted neighborhood. Okay, now you can see that this is 0 and this is epsilon. So this circle is in between those two annular regions. Okay, that annular region, and f is analytic here, right? Therefore we can have, what are the coefficients of bn's are given by, so the coefficients of bn's are given by using this integral 1 by 2 pi I times, that we will write here. Yeah, now therefore this bn's can be written as, bn's can be 1 by 2 pi I times integration of f of z, z minus z naught whole power minus n plus 1 dz over c, where c is here, our c is a unit circle, not sorry, unit circle, it is a circle with radius rho, right? But already it is given that f of z is bounded. So f of z is bounded, so if you take the modulus of these values, modulus of bn, that will become less than or equal to 1 by 2 pi into modulus of these values, and f is bounded. So suppose say it takes maximum value m, then z minus z naught is precisely rho, right? So this will become rho power minus n plus 1, and length of the curve. Length of the curve is circle with radius rho, so therefore it is 2 pi r. So here 2 pi r, right, which is rho. That is same as saying that 2 pi will get cancelled. M into rho power this minus n, if it comes to numerator, it will become rho into m into rho power n, right? Now remember, this right hand side we can have rho as small as possible, which is close to 0, then this tends to 0 as rho tends to 0. Therefore, all these coefficients left hand side, whatever we are having, they all should be equal to 0. So that shows that Bn equal to 0 for all n. That means we have taken a Laurent series expansion and we have shown that Bn's are equal to 0. That means there is no principal part. Hence, that singular point is removable singular point. This result is due to Riemann. Now we'll come to the last result, which is Kasowiti-Weierstrass theorem. This is very interesting result, which says that suppose our Z naught is essential singularity. If our Z naught is an essential singularity of F, and if you then there is for any positive so what I can want to say is that then there exist are given if it is there, then there exists some deleted neighborhood of Z naught, some deleted neighborhood of Z naught, okay, deleted. So we'll write like this, such that here if you give any complex number, okay, be any complex number, then there exists a point in this such that f of z is equal to w approximately, okay. That means if you call it this is w naught, then there exists some z in this neighborhood such that mod f of z minus w naught is less than epsilon, and it is true for any epsilon you give. That means we can approximate every complex number by some value of f coming, that z is coming from this neighborhood, okay. That means again let's understand, if z naught is essential singularity, then there exists a neighborhood of that z naught where give any complex number, I can give some z from that neighborhood such that f of z is very close to that w naught, okay. So every complex number has some approximation of from this f in this neighborhood. That is the very strong result, okay. Fine. How we'll prove? We will prove, of course, by contradiction. That means, suppose what we want to prove, given you give me any epsilon, then I can find one z from this neighborhood. There is some neighborhood such that there exists one z such that mod f of z minus w naught is less than epsilon. This is false means what? There exists one deleted neighborhood, okay. This is true satisfied at some point z in each deleted neighborhood, okay. Not only some neighborhood, it is true in each deleted neighborhood, okay. Fine. So how we will prove this one? We will prove by contradiction. Suppose assume that there exists a deleted neighborhood, okay, such that this whatever z you take here, the f of z, distance between f of z and w naught is always greater than or equal to this epsilon, okay. So an epsilon is given. For this epsilon there exists some delta, that means there exists some neighborhood in which this condition is not true. That means for every z you take in that neighborhood, mod f of z minus w naught is greater than or equal to epsilon, okay. Fine. So the distance is at least epsilon in that neighborhood, okay. Now of course we can select this delta such that f is analytic throughout this f. We can select not only this delta exists, we can make sure that this delta in such a way that this f is analytic throughout this deleted neighborhood z minus z naught less than delta. Why? Because from here you will have one delta, and because this f has this z naught is essential singularity, right? So therefore it is an isolated singularity. that means there exists. What is meaning of saying that it is an isolated singularity? We can find a neighborhood where except at that point remaining everywhere it is analytic, right? So there exists some neighborhood that is, you can call it as delta prime, such that f is analytic throughout that deleted neighborhood. Now among delta and delta prime, whichever is smaller, you take that and you call it that as delta. Okay, so whatever delta we are getting here, in that delta or without loss of generality, we can assume that our f is analytic in that deleted neighborhood. Okay, if this delta is different, as I explained here from this part, we can see that you will get another delta prime, then take the minimum of delta and delta prime, then this both conditions are satisfied. That means f is analytic in that neighborhood, deleted neighborhood, and this f of mod f of z minus w naught is greater than or equal to epsilon in that neighborhood. Okay, now with respect to this, and see, epsilon is always greater than 0, so therefore this is strictly greater than 0, it is non-zero. The absolute value of this one is non-zero. Okay, so whenever we have this, the obvious idea is going to the inverse of this function. So define g of z as 1 upon f of z minus w naught. So if you define g of z as this in this neighborhood, okay, then because f is analytic here and f is non-zero here, so therefore g of z, this is also analytic here. And what can you say about mod g of z? Analytic, and mod g of z, which is equal to modulus of this one, but this is greater than or equal to epsilon, so this is less than or equal to 1 by epsilon. That shows that this g of z is bounded. Okay, so g of z is analytic and g of z is bounded where? Bounded in this neighborhood. So by previous theorem, which is lemma, Riemann's lemma, what we know, this point z naught is essential singularity of f. Okay, so we can see that then z naught is a removable singularity of g. Okay, right? Fine. See this this g problem is wherever f is not analytic, then this is also not analytic at this point, right? So clearly z naught is a singular point for z naught is a singular point for z also. So therefore it will become removable singularity for z, this new function g. So therefore what we can write here is that by previous lemma, this z naught is a removable singularity for the function g or g of z. Okay. Now whenever we have a removable singularity, then what we know is that we can define, only problem is at z naught, so we can define g of z naught in such a way that g will become analytic, right? At z naught. So by defining g at z naught suitably, we can get that g is analytic at z naught, right? So define in such a way that, okay, such that g will become analytic at z naught. Okay, that is not a problem, because whatever Lorentz series expansion is there, that constant coefficient whatever is there, you define that, right? Now there are two cases, this, because this g of z, it may be equal to 0 or it may be not equal to 0. Okay, so in either case we will show that there is a contradiction, then we will have a here. Why? If at all, if g of z naught is equal to 0, so if g of, so I'll write here, if g of z naught is equal to 0, then this obviously z naught is a 0 of order m. Why it is 0 of order m? That is because if you remember, our this g is analytic, okay, at z naught, and g of z naught is equal to 0, and this g is not identically equal to 0 in this neighborhood, which is mod z minus z naught less than delta. So therefore what we can see is that itself shows that this whatever result we have proved, that shows that this z naught is a 0 of order, say some m. Let me show that result where we have proved, so that we'll get an idea. Here. See this g is analytic at z naught, we know, and g of z naught is equal to 0, and g is not identically equal to 0 in any neighborhood of z naught, that is that is how we have defined, because it is greater than 0, right? Therefore, g of z is not equal to 0 throughout some deleted neighborhood of in this theorem. If you see this proof, what we have seen here, if you see this proof, right, if at all if fn of z not equal to 0 for all n, then we get that f of z is equal to 0, right, which is not true, because it is not true, it is not equal to 0 in any neighborhood, right? So that shows that this z naught is a 0 of order k, right? So this much part we are using here, that if g is analytic at z naught and g of z naught is equal to 0, but g of z is not identically equal to 0, then what we are having here is that z naught has to be a 0 of that of some order, call it m, for that function g. That is what we are using here, right? Yeah. So therefore z naught is a 0 of order m for this function g, right? This is again equal to 0 in this, right? Yeah. So therefore, because this is a 0 of order m, we can write this g of z, as z minus z naught whole power m into, you can call it some phi of z, where phi of z is analytic at and it is non-zero at z naught. Okay. So therefore, what is our f of z will become, because f of z, you can write it this as 1 by g of z, okay, 1 by g of z plus w naught. Then this g of z you substitute as like this, z minus z naught whole power m, this f of z where in the deleted neighborhood, that means when z is not equal to 0. So you can write here, if you want, when z not equal to z naught, or in this neighborhood you take, okay. Fine. You write here, so that you may think that why g of z is coming here, and then we can write in this way. Then you simply substitute g of z value here and further simplify whatever you get in numerator, that you simply call it as psi of z, okay. Then you can check that where psi of z is this, you can check that psi of z is analytic at z naught, and psi of z naught, which is simply this term, will get 0. So 1 by phi of z, 1 by phi of z naught, we know it is non-zero, okay, because the way it is phi of z is analytic and non-zero at z naught. So therefore 1 by phi of z is not equal to 0. That shows that what we have proved is that this f of z, if you observe here, what we have proved is that f of z is psi of z upon z minus z naught whole power m. We are able to express this f of z in this form, where psi is analytic and non-zero at z naught. So therefore this z naught will become a pole of order m. So z naught is a pole of order m for this f, which is a contradiction, because our z naught is a given to be essential singularity. So if z naught is equal to, g of z naught is equal to 0, we are getting a contradiction. Suppose g of z naught is not equal to 0. So that is, I think here we have explained. Okay, go back here. That means our second case is this much. If g of z naught is not equal to 0, then we can write this f of z as 1 by g of z plus w naught, okay, which is analytic, okay, because if g of z naught is not equal to 0, f has only problem with z naught. Then at z naught, this 1 by g of z naught, which is non-zero, so you can see that it is analytic at z naught by defining our f of z naught as 1 by g of z naught plus w naught, because only at problem with z naught, right? So simply define f of z at z naught is 1 by g of z naught plus w naught, okay. Then it will become f will become analytic even at z naught, right? So if you can able to make it that function analytic at that singular point, then that singular point will become a removable singular point. So you will get that z naught will become removable singularity of f, but which is a contradiction, because our given singularity is an essential singularity. So whether g of z is not equal to 0, if g of z naught is not equal to 0, we get contradiction for we'll get a conclusion that z naught is a removable singularity, which is a contradiction. If g of z naught equal to 0, by simplifying further, what we will get is that z naught is a pole of order m for f, that is again a contradiction, okay. So these both cases should not happen, they cannot happen. That is because we have assumed that there exists some deleted neighborhood which happens such that this is happening. Okay, so therefore this supposition is wrong. So this supposition is wrong means this is true, right? So you give me any epsilon and given any complex number, then there exists some z in this any dilated neighborhood such that mod f of z minus w naught is less than epsilon. Okay, fine. So these are all about how the functions behave near singularity. Okay, we'll stop here and we'll see in next class. Thank you.